Dear ladies and gentlemen, now I'm going to present you the analyzer mode of the DC-23 data collector and vibration analyzer operation. So the analyzer mode allows you to make off-route measurements or data collection with any setup that you would like to do. The analyzer mode, it includes measurements of autospectrum, envelope spectrum, overall levels, amplitude and phase, time signal, constant percentage bandwidth spectrum. This is something like 3rd octave or 1/6 octave or 1/11 octave spectrum. Cross spectra, orbits. But there are two unique features to this instrument. One is the combined measurements. With the combined measurements you can measure simultaneously and synchronously two spectra from each channel of the instrument. We have two channels, so you can make synchronous and simultaneous measurements on the two channels. And in the combined mode you can make measurements of autospectrum, envelope spectrum, rotation speed, and overall level for the two channels. The other interesting feature is the ISO measurement. This is measurement according to ISO standard and evaluation of the machine condition according to this standard. So we can just start from this. Once you go to the ISO mode, you see that you are going to measure according to ISO 10816 Part 3 standard for the machine of group 4 on rigid supports from 10 to 1 kHz RMS millimeters per second. And this is the chart for the machine condition zones. Zone A is a new machine. So if you purchase the machine, paid for the installation of it, for machine commissioning, you may think that it will be in the A zone. The B zone is a good machine that doesn't have any restrictions on operation. Zone C, this is machine in alarm condition. It means that you cannot continue its operation forever. You have a limited time of operation, usually it is 1 month, that you have to repair the machine to bring it down to the B zone. And the D zone, this is the danger, and it means that you have to shut down machine immediately, otherwise it can be destroyed by the vibration. So, these numbers are taken from the ISO standard. So how we do the setup? We go to the setup button 4 and we select the standard. We have here a few standards. For example, we can take this ISO 816 Part 3. This is for general industrial machines operating between 120 and 15,000 RPM. You can read it. We select the machine group. This is the size and the power from a very big machines to relatively small machines. We have quite a small demo stance here, so we select the group 4. We select supports rigid or flexible. So we can say that this is quite flexible, but flexible it means that the machine works above the first resonance, above the first critical speed. Rigid, it means that the machine operates below the first critical speed. So this is important and it's written in the standard. Then we select the bandpass filter. Previously, the ISO standards, they had only two bands for the analysis. One is for slow rotating machines from 2 Hz up to 1 kHz. This is for machine rotating below 600 RPM. If your machine is quite fast, above the 600 RPM, then you take the band from 10 Hz. The higher the frequency, the faster is the measurement. Additionally, now in the standard it is written that if you have some gear mesh frequencies or some blade pass frequencies that are above 1 kHz, you can increase the frequency band. So it's possible to do it up to 5 kHz, up to 2 kHz, etc. But we don't have here anything like this. Then the choice is between microns and millimeters per second. If we take microns, detector type is only root mean square, apply it. Then we will have this zone in microns. So this is micron from 11 up to 36 microns. This is the zone limits. If we go and selected in millimeters per second and apply it, the thresholds will be taken in millimeters per second. So this is more convenient. So the machine, according to ISO 10816 Part 3, Group Number 4, rigid supports 10 to 1 kHz RMS millimeters per second. We have 1.4 AB zone, 2.8 BC zone, etc. So we can start the measurement. We start our machine and we have a choice. Measure by channel A, by channel B, or by 2 channels. So we press enter and start measurement for the 2 channels. So it takes about 2 seconds for measurements and some data processing, and here is the result. So the second channel is here, though this is the B channel, and it is in a good condition and it has vibration level of 1.6 millimeters per second. This bearing is a bad one and it is in the alarm condition and it has 3.4 millimeters per second. We can try to do an experiment. We can, for example, make it more flexible. Just remove the load from the bearing and it will be like this. And we can start the machine. Save the measurements and make measurement again. 2 seconds of data acquisition, a little bit of processing, and here we are. Of course, if it is more flexible, we have much more vibration, you can even see it. And it is already 5 millimeters per second. So in this condition, this machine cannot operate. So we apply our load back and continue. So here you can save the data for the database and for future trending. The second key feature of this instrument is the combined measurement, as I told you. So in the combined measurement, we have simultaneous measurements of autospectrum, overall level, envelope spectrum. Additionally, we can make measurement of the rotation speed. So here we can do the setup of all the measurements. For example, for autospectrum we can select the maximum frequency up to 51 kHz. We can select the frequency resolution of the number of lines up to 51,000 lines. So this instrument can work up to 51,000 lines and to up to 51,000 Hz. But this is very rare measurements. For this machine we select just a normal one, 800 Hz by 400 lines. It will be much faster. And we can select the different scales. Overall level. This instrument also has very many different bands for overall level. It is up to 25 kHz, and these high frequency measurements are used for the bearing diagnostics or the friction force diagnostics. We select just a normal one, the standard. We select it in millimeters per second, like in the standard RMS linear averages or linear scale. If we go for the detector, we have also true peak measurement, or we can have peak from RMS. So this is quite a standard thing. We have kurtosis coefficient, we have peak factor coefficient, so you can do a lot of different things with this instrument. The scale is linear or in dB. Envelope spectrum, let's do the same. We also have very many different bands for demodulation, so that to tune to the bearing signal. For this one, I select just a 12 kHz, so this is quite a high frequency. For the high frequency, we'll see the difference between the two sensors, between the signals from two sensors, as the high frequency vibration doesn't penetrate through these joints, like here. These joints will stop it, and we will see a different signal. So this is for channel A. We can do the same for channel B. So that we can compare the signals from the two channels. You can also set different setups and put sensors on the one and the same bearing, and then you will have much more parameters to analyze. So I make just the same setup. Averaging type can be exponential, peak hole, linear, etc. etc. I just use the linear, and as we measure envelope spectrum on high frequency, this is quite a random signal, and we need some averages to get the better readings. So now we have set up for channel A and for channel A and channel B the same numbers, the same setup, no difference, and we are ready to start. We have one sensor on a bad bearing, one sensor on a good bearing, and we start the measurement. So first it collects some time domain data, and now it is processing it. So it collected the data from the two channels simultaneously and synchronously, plus it makes readings from the cathode, and now it presents the spectrum. So what do we see here? We see here envelope spectrum. This is envelope spectrum from the two channels, and we see that envelope spectrum is completely different. Here we have some lines, and this is a bad bearing. That's why here we don't see any lines. The distance is 5 centimeters, but the result is different. We have overall level at the selected band from 10 Hz to 1 kHz, 2.8 on this bearing and 1.5 on this bearing. And we have the rotation speed reading. This is in RPM 2971. So I have an induction motor of 3000 RPM, and we have some sweep frequencies, so this is what you see. We can also see the autospectra from the two channels. For this we press the button and we see autospectra, and this is envelope spectra, this is autospectra from the two channels. So you see that autospectra are more or less the same. Though the envelope spectra, high frequency spectra, we have finished our measurement, so I stop it. So we see that envelope spectra are very different. This is high frequency, it doesn't penetrate through these joints. The lower frequency, the autospectra, are the same, more or less the same. The levels are a little bit different, but the shape is more or less the same. We can also see spectra from one channel. So this is channel A, and we have autospectrum and envelope spectrum, we can analyze it. This is channel B, and we can see autospectrum, envelope spectrum from channel B. So this is very convenient, and you can do the analysis of it. For example, we go to channel A, and we see the autospectrum. We can go to see the envelope spectrum. This is more interesting, and this is the envelope spectrum. And we have a special analysis mode. For example, we go to the analysis mode. We select the model of the bearing. Here I have the bearing of the model of the type 18. I can select a different one from any files that I have here that I downloaded from the computer. Select the bearing model. Here it is, bearing type 18. I apply it, and now I have the frequencies. 4. So this is the list of the bearing frequencies. It starts with RPM, so the rotation speed. I would say that I do not see any RPMs here. Maybe here is the second harmonic of the RPM. That means that there is some kind of a misalignment in the bearing. That's very possible. Then I see FTF. This is fundamental train frequency or the cage frequency. Actually nothing here. Then I see ball spin frequency. Also not here. I see the BPFO. Yes, the BPFO is here. I just need to switch it one maybe channel. And this is BPFO. So I have a problem with the bearing. I have BPFI. It is not here. So the diagnostics will tell me that this is BPFO and this is the problem of the outer race of this bearing. Additionally, I see that I have some modulation of these frequencies. Let's find what is the modulation frequency. I remove this, and here I have the sidebands, and I see the frequency of the main cursor. I put it here, and I adjust the bandpass, or not the bandpass, I adjust the sidebands like this, up and down, and here it is 18 Hz. I see that I have modulation on 18 Hz. Bring back the frequencies. 18 Hz, this is FTF, this is cage frequency. So I would say that I have BPFO modulated by FTF. So the diagnosis will be that I have a crack on the outer race and I have problems with the balls. Usually such picture it represents a situation when you have balls of different sizes. One ball is weird more than others, and that's why you may have a picture like this. So that's it. We can save the measurement. So this was one of the modes of the Offroute or analyzer mode of operation. I would like to say that there are actually two modes of operation. One mode is this analyzer mode, when you can select any type of measurement you would like to set up it and do the measurement. And then you will save it in a file that you can name. So here I have a list of the measurements that I have done and I have saved. By default it is written the setup and the date and time of measurements. You can also add your own name to the saving of this file. But there is another option. The other option is that you go to the root. If you have some root here and you have already the structure of your enterprise or your company, for example, I have this demo stand and I decided to measure not only the measurements that are in this database that are programmed to be measured, but I would like to add some more measurements. Then I can do this as well. I can go to the alternative menu and I can add additional measurement task like this. And in this way I can measure all the same measurements that I did in my analyzer mode. For example, I can go to the auto spectrum and measure it with a different setup. For example, I want to have it with something like 25 Hz or very slow one with a very many lines with very high frequency resolution, and I can do the measurement. It will take a lot of time, of course. Or I can do it vice versa. I can measure it up to 12 kHz or up to 604 with the frequency resolution like this. This is the number of lines. I can do like averages like 4 linear scale and in millimeters per second, like this. This is the reduced measurement time. It means that it will make the measurements and only then produce the results. It is much faster. Or I can see average by average. I can start my machine and do the measurement. So this is 2 seconds for one average 1 of 4, and this is my spectrum. So of course in millimeters per second I have only lower frequencies, I do not have the higher frequencies, but anyway I can do this. So the measurement is completed. I can zoom it like this and see the spectrum that I have. Of course I can here also change the units. So I can make it in dB by pressing 1. So this will be the same spectrum in dB. I can go back to Gs, like for example here, this will be in G's. I can see it in mils, so this is micra inches. It will be like this. So this is the mode of also off-route measurements, but it will be saved to the point in the route. So you may have just a database of routes of your enterprise, and you may not even make the measurements on the route data, or you may have no measurements in the route, but you can go to off-route measurements and save it in this database structure. In this case, in this bearing, you will have the additional measurements, and when you will unload it to the database, it will be stored in the exact place of your database. So this is additional feature of this instrument, so you can do off-route measurements inside the route and store it in the exact location of the database, or you can do just the off-route measurements, download it to the computer and then distribute it through your database, through your structures. So thank you very much for your attention. This was the DC-23 vibration data collector and analyzer, the analyzer or off-route mode of its operation. Thank you.